Hello everyone. So we already have started different fabrication techniques. In our last lecture we have seen what are the different PVD techniques, that is physical vapor deposition techniques, and then we also have seen that the widely used PVD techniques are thermal deposition, E-beam evaporation, and then sputtering. All three techniques are used in device fabrication, in various device fabrication including sensors. Now we will slowly move to the next deposition technique, which is known as chemical vapor deposition techniques. So in physical vapor deposition technique we have seen what is thermal evaporation, we have seen what is E-beam evaporation, we have seen sputtering technique, and then in sputtering technique there are different other classification. For example, one can be DC sputtering, one other type is DC magnetron sputtering, and then have RF sputtering. So based on the source of creation of that plasma inside a sputtering chamber, we change the name of the sputtering technique. However, the basic principle of sputtering technique is already been discussed. Now we will discuss chemical vapor deposition technique. Just like physical vapor deposition, in chemical vapor deposition also you will find there are various types of chemical vapor deposition techniques. So here I have listed three. There might be there are few other chemical vapor deposition techniques as well, but widely used chemical vapor deposition techniques are atomic pressure CVD, low pressure CVD, and plasma enhanced CVD. These are the three major classifications of chemical vapor deposition technique. Now from this two term it is very kind of evident that the chemical vapor deposition technique in these two are related to the pressure associated with the process. Atmospheric pressure CVD will use a pressure which is similar to atmospheric pressure. In case of low pressure CVD, the pressure used inside the chamber will be considerably low. So that's why they are named as atmospheric pressure CVD or APCVD, and low pressure CVD, that is LPCVD. Then we have plasma enhanced CVD, where again from the name itself it is very clear that plasma will be created inside a CVD chamber in order to deposit thin film materials on different substrate. Now here I have shown the scheme of a chemical vapor deposition technique. So unlike physical vapor deposition, in case of chemical vapor deposition technique we use multiple gases inside the chamber. So there is a chamber inside, or there is a chamber in chemical vapor deposition technique as well. We had a vacuum chamber in case of physical vapor deposition, but in this case we use a chamber which has a gas inlet and a gas outlet. In this case the gas inlet is used to introduce gases inside, and then we introduce multiple gases as per our requirement what we want to deposit on a substrate. So here this is the substrate, we keep on substrate, and then we maintain different condition inside the chamber so that the gases that are entered, different gases inside the chamber will perform a reaction, and then the desired material will get deposited on the wafer. So this is the basic principle of a chemical vapor deposition, and the condition inside the chamber will be decided based on the reaction that is involved in this deposition technique. Then once these gases and different materials react, there will be different byproducts. So these byproducts will go out using that gas outlet. So that is how it is designed. So there will be a gas flow, there will be multiple gases, and then there will be a reaction that will lead to a deposition of material on top of a wafer or a substrate. So if we compare, in case of PVD, it's directional deposition. What I mean by directional deposition is, if you have a target or if you have a say source, then the deposition will be always in this direction, that is in the topwards direction. So the evaporation will take place and all deposition will be in this direction, and finally you will get a thin film on a substrate. However, in case of CVD, you will find it's a multi-directional deposition. What do you mean by multi-directional deposition? For example, if you have say a wafer kept like this or a substrate kept like this, you will find because it's reaction happening everywhere, so the material will get deposited in all the directions because it depends on the reaction, and the reacting materials are gaseous in nature. So the gas will move all around and then it will help depositing that particular film in all the directions. That's why it's a multi-directional deposition. However, in this case the deposition is always in one direction, that is in the upward direction in case of PVD. And because of that directional deposition, you will find that the deposition is non-conformal. So what I mean by non-conformal is, if you have a substrate like this, a pattern substrate like this, and if the direction of deposition is vertical, you will find that materials are getting deposited in these areas properly, but in the sides there will be less deposition or almost no deposition, because the deposition is in vertical direction, material will not get deposited in the sides or edges. That's why the deposition is non-conformal. However, in case of CVD, you will find if you have a pattern substrate and because it's like gases are going everywhere and reacting, gases are going in different directions and reacting, you will find in all the direction the depositions are taking place. So it's like a conformal deposition. So CVD will lead to a conformal deposition. However, in PVD the deposition will be non-conformal. So one of the major difference that we have said is, unlike PVD, in CVD vapor generation is not required as the species are already in gas or vapor phase. So in PVD you need to generate the vapor from the source material, that is the gaseous form of that material, so that it goes upwards and then get deposited on the substrate on top. However, in case of CVD you are introducing gas itself, so you don't need to generate vapors. These gases, multiple gases, will be reacting with each other and with the wafer or substrate, and then the material will get deposited on the substrate. So there is no need to create vapor inside the chamber. And second thing is, the deposition in PVD is directional. So if you have a source below, so always the deposition will happen on the topward direction. However, in case of CVD, it's like multi-directional, because there is a gas. For example, if this is the substrate, if there is a gas around, so deposition will happen in all the sides. So you will get a conformal deposition, but in case of PVD the deposition will be non-conformal, right? Now this leads to a good step coverage. Now what is a step coverage? In this image it is much clear. For example, if you have a substrate which has different patterns like this, as it is shown, say here there is certain sort of pattern, here there is a pattern, and then there is a groove in this. Now if there is a point source, which is the case in case of PVD, you have a source and then the deposition is like directional, in that case you will find that deposition at different sites will be different. For example, because it's a point source and it's a directional, in here you will find the depositions are okay because the materials are coming in contact with the substrate directly, and that's why the depositions are taking place relatively at a higher rate compared to other areas of that substrate. And in certain places, because it's a directional, the materials will not reach. For example, in these areas, materials will not reach. In this area, material will not reach. So there will be no deposition at all in this case. And because this feature is shadowing out this area, so it's like a line of sight deposition. The material will not reach in this area, so there will be no deposition in this area. And that's why you will find a non-uniform deposition in the pattern substrate. So the step coverage, that is covering these steps, are not very good. That's why we also have discussed in the previous slide, it's a non-conformal deposition. However, in case of CVD, there will be gases around, so gases will go in every place, and hence you will find the depositions are conformal throughout, even if it is a pattern substrate. So this is one of the biggest advantage of CVD deposition. Now, chemical vapor deposition also has various processes involved. So I have mentioned the processes over here. So there are 7 different stages of chemical vapor deposition. The first stage is transport of reactants in the reaction region. So one thing that we already have discussed is there will be a gas flow inside the chamber. Multiple gases can be there. So the first stage is transport of reactants in reaction region, that is forced convection. So you will forcefully insert gas inside the chamber. This is the first step. The number of reactants can be higher. There can be gas A, gas B, gas C, so on and so forth, right? The second stage is transport of the reactants on the substrate. So now the gas that is entering will be transported towards the substrate, that is where your substrate is kept. Now this is the second stage of the chemical vapor deposition. In the third stage, the substrate will absorb the gases on the surface, that is the reactants on the surface. So this is what is the third stage. So gas molecules will come and get absorbed on the surface. Now in the fourth process, different surface phenomena will take place. For example, chemical decomposition, surface migration, site incorporation, so on and so forth. So there will be certain sort of reactions on the surface which will lead to a deposition of a desired material. Then in the fifth stage, the desorption of byproducts, because it's in reaction or a reactive system. After the reaction, you will find there are several byproducts in the chamber. So in the fifth stage, all these byproducts will get dissolved from the substrate. Then transport of the byproducts through boundary layer, that means it will slowly leave the boundary layer, that is the reaction region, and finally transport of the byproducts away from the deposition region. So this is the deposition region, this is the chamber, so it will go out of the chamber in the seventh stage. So these are the basic 7 stages associated with chemical vapor deposition. Now, because it's a reaction based system, you also can create different proportion of different materials in the deposited layer. So what I mean by that is, if you have say 2 gases present inside the chamber, say gas A and gas B, and if you want the deposited layer to be say A2, B4 or B3, this is possible just by changing the proportion of the gases present inside. Even if you want A 1.5, B 2.5, this proportion is also possible. This can be A or B, this can be A, B, C, or different other materials. So different combinations are also possible, but you have to first decide what should be the proportion of gases that one should insert inside the chamber, what should be the temperature inside the chamber, what should be the different other conditions associated with the reaction inside the chamber. Then only you will be able to get the desired deposition. So this process also needs a optimization, and optimization in this case is not only the physical parameters like temperature, pressure, so on and so forth. It also like chemical parameters like what kind of gases you are inserting, what should be the proportion of these gases. So, optimization wise, this process is bit more complex than PVD, because in PVD you just need a source material and then you usually optimize the different physical parameters inside the chamber like vacuum, time, pressure, so on and so forth. But in this case, some chemical parameters also needs to be optimized. Chemical parameters is in the proportion of different gases and so on and so forth. Okay. Now, CVD is a technique to deposit thin films on a substrate that we already have seen. So, the ultimate purpose of CVD is to deposit thin film on a substrate. So, source gases are introduced to a reaction chamber, that is different gases involved in depositing different material will be inserted inside the chamber, and then energy is applied in terms of say heat, RF power or similar energy that can facilitate the reaction process. This will decompose the source gases, that is the gases that you have inserted for deposition. Reaction of the chemicals will then form a thin film on top of the substrate. So, this is the basic principle. I also have explained different processes involved in the previous slide. So, in short, this is the process that we usually see in case of chemical vapor deposition. But in this case, the process is a high temperature process. So, you will find the reaction chamber, the temperature inside the reaction chamber can go or vary between 600 to 1100 degrees centigrade, similar range. In that similar range, usually people maintain the temperature of the reaction chamber, and that temperature actually helps in facilitating that reaction. It depends on the kind of reaction that you want and parameters associated with that. Now, here I have again showed the classification of chemical vapor deposition. So, chemical vapor deposition can be classified based on pressure or based on the stimuli that is present. So, as far as the pressure is concerned, you will see that CVD technique can be classified in atmospheric pressure CVD, low pressure CVD or ultra high vacuum CVD. I already have discussed this in the beginning of this lecture. So, based on pressure you can classify the CVD process. It can be atmospheric pressure CVD, it can be low pressure CVD or it can be ultra high vacuum CVD. Similarly, CVD process can be also plasma enhanced or photo initiated. Photo initiated and plasma enhanced meaning the stimuli is now different. So, either you create a plasma inside in order to deposit materials, or this can be photo initiated. For example, you apply UV light in order to initiate the reaction. So, this can also be stimuli based. So, these are the various types of CVD techniques. Then there are various other CVD techniques like high density plasma CVD, where the density of the plasma will be higher, and there is one more deposition technique which is known as atomic layer deposition or ALD. This is also a kind of CVD technique, but in this case you insert the gases sequentially inside the chamber. So, this is a kind of CVD technique, but a bit different. With this particular technique you can create very thin layer of films, a very thin layer. If you want, you should use atomic layer deposition technique. But in all these processes the basic principle is same. The 7 different process or steps that I have shown, these steps will be followed in all these CVD techniques. Now, because plasma enhanced CVD is bit different than what we have seen, that is why I am discussing a bit more about plasma enhanced CVD. Otherwise, the basic principle is like that 7 step that we have discussed, but in case of plasma enhanced CVD, there will be parallel electrodes. One is grounded, another one is RF energized. So, this is RF energized and this is grounded. Now there will be a capacitive coupling between the electrodes, and that excites the reactant gas to plasma. Once you apply enough RF power, you will find the gas present inside the chamber will become plasma. Plasma meaning the gas will like get ionized. What is a plasma? I already have said during sputtering, it is a fourth state of matter. So, like liquid, gas, solid, you also have plasma. So, high RF power in this case will create a plasma inside the chamber. Now, substrates are placed between the electrodes, and we heat the substrate to 250 to 350 degree centigrade. Here this wafer is the substrate and it is placed in between the electrode 1 and 2, and then there is plasma in between the electrodes, but usually the CVD temperature is required 600 to 800 degree centigrade. But in case of this plasma enhanced CVD, the temperature can be a bit lower. Okay, so it's like a low temperature deposition that helps to avoid substrate damage. So, as we have said that CVD is like an high temperature process, but if you want to deposit something on a polymer substrate, or if you want to use say biomaterials, polymer materials, organic materials, then you need to think about the temperature as well. So, in these cases you want a low temperature process so that your substrate is not damaged. So, plasma enhanced CVD can help you in this regard. So, it is a low temperature deposition. The plasma inside will then help the reaction, and then it will the desired material will get deposited on the substrate. Now, the deposition rate in this case also is considerably high because it is in plasma, already atoms or molecules are energized. So, it will facilitate the reaction more. Then in this case you will find the uniformity and the quality of the film is quite good. What I mean by the quality is like, for example, if you have a substrate, say this is the substrate, and you want to deposit say one material on top of that, say the width of this deposited material is like say 15 nanometer. So, a good quality film will show a smooth surface, no defects. There will be less defects. I mean, there will be no such defects, and the thickness will be kind of uniform throughout. So, the uniformity also will be great in case of a good quality film. Then this also will help a conformal deposition, just in case if you have a pattern on the substrate. So, it also has a sufficiently good conformal deposition, or it will ensure a conformal deposition on a pattern substrate as well. But one disadvantage of plasma enhanced CVD is it creates unwanted byproducts which may lead to contamination. So, the unwanted byproducts anyways needs to take out of the chamber. So, there is again a kind of optimization needed. Sometimes that unwanted byproduct may lead to a contamination in the deposited film. So, out of many different options that we have for deposition, we have discussed some of the PVD and CVD techniques. So, in this, the one that we have recently discussed is associated with the CVD technique, and as far as the fabrication process is concerned, it's very important to understand what fabrication technique would be suitable for certain device fabrication. I probably have discussed the parameters that one should think before choosing the fabrication or deposition technique in specific. So, as far as the PVD is concerned, we have seen that in case of PVD, you need a vacuum chamber, and then in that vacuum chamber, you can either go for thermal deposition, then EV evaporation, or sputtering. So, all three techniques we have seen to some extent, and how these three techniques are different from each other. However, in this case, in case of PVD, One thing that we can say is the chances of contamination is very less, because in case of PVD you don't actually have any other material present during the deposition. I'm talking about an ideal situation where, say, this particular chamber is very new and you started a deposition of, say, gold. In that case, the chances that that gold will have some other contamination is very less, because there is no other material present. But again, we have also seen that if you are using filaments of different material, if there are some other material deposited previously, in that case the chances of contamination increases. But if you think ideally, if everything is fine and everything is not interfering whatever is associated with this technique, then the only material present in the chamber is the material that you want to deposit and then the substrate, right? So in that sense, the chances of contamination is fairly low. But in case of CVD, in the inside the chamber you actually insert different gases, right? One or two gases, say gas A, gas B, then they will react inside the chamber, and then they'll deposit some material on top of the substrate. So this reaction inside the chamber will also generate, say, different byproducts XYZ. These byproducts may get deposited on top of your film. So in principle, the chances of contamination in case of CVD is there. In principle, I'm saying, although if you have a good outlet mechanism, things will go out very easily from the chamber. But if you look at the process, that multiple gases are coming in, they are reacting, and out of that reaction you have several byproducts, several kinds of byproduct. So the chances of contamination in that case is a bit higher. So these are the parameters that one can think. And secondly, if you have a pattern substrate, I already have said, that it also depends on the kind of substrate that you have. If you have a pattern substrate, then it's better you use a CVD technique, because then you'll get in conformal deposition, right? Now again, if you don't need a conformal deposition, you can go ahead with PVD as well. That's not a problem. So this is how one can decide. These are the things that probably will help someone to decide which deposition technique one should use. Apart from that, I also have briefly mentioned the advantages and disadvantages associated with the different deposition techniques, and you can choose the method of fabrication based on that deposition technique. So before you go or decide upon the fabrication associated with the sensor that you are making, it's better that you first also decide which technique you are going to implement, and then you can actually decide the process flow. So everything is associated with the process flow. You may find that CVD is better option in case of a certain sensor. Although you have an option of PVD, you can also go ahead with PVD, but CVD is giving you a better film thickness, film uniformity, and quality of the film. But PVD may be the best suitable one as per the theoretical analysis, but in practice this can be a bit different. That's why it's very important that you understand the basics of deposition before you decide on the deposition technique. Hope this particular discussion would help you in this direction, and in the coming lecture we will also see some other technique associated with microfabrication. So there are three take home messages from this. So CVD needs one or more chemicals in the chamber. So mostly the chemicals are gases. So there will be one or two more gases present inside the chamber. Then CVD provides good step coverage, which leads to a conformal deposition. We already have seen if there is a pattern substrate, then CVD will ensure that the deposition is like sort of conformal across the substrate, and it also will provide good step coverage. Then there are different types of CVD reactors present. So this is one type of reactor that we have seen in case of plasma enhanced CVD. Then there are various types of reactors also present in CVD based on the requirement, but the process associated with the CVD is more or less the same that we have discussed. I only discussed plasma enhanced CVD separately because it has a extra step of creation of plasma. That's why I thought it would provide a different perspective towards that deposition technique. Otherwise, the deposition technique is more or less same in most of the processes, and people use different types of reactors. It can be in a tubular furnace, it can be in a furnace where different heating stages are there. So you'll find a bit complexities are associated with the reactor, but the process is more or less same, and reactors are designed based on the kind of deposition you want. So in upcoming discussion we will see other deposition techniques. Till then, thank you.